Hi everyone. Today I wanted to look at the topic of learning in senior mathematics. And the reason I think it's really important to look at learning is because this is the bread and butter of your job if you're a teacher. One time they interviewed a guy who was the best drill salesperson in the world, or something like that. And they said, what's the secret of being a great drill salesperson? And he said, well, you've got to know your business. And so the interviewer said, so you know everything about drills? And he said, no. I said, I know everything about holes. And it's a bit like us for teaching. If you're becoming a teacher, the only reason you're a teacher is because you have to help people learn. If no one's learning anything, no need for a teacher. And people can learn things without a teacher, but there's no point teaching if there's no one learning. So learning is fundamental to what we do. It's the key part of what we do. It's the most important thing you should understand as a teacher, how kids learn. Now the problem we've got is we don't really know the answer to that. We've got some clues and I'm going to talk about those today, but there's no recipe. So the first way we've thought for a long time about people learning, and this started in about 100 years ago actually, was what we call behaviourism. And some of you would have heard of Pavlov's dog and some of those sort of experiments. Famous theorists like Thorndike and others who developed this method, and really it still pervades quite a lot today. This is a traditional method where teachers transmit knowledge and known facts to the students. The students then record these in their textbooks or in other places, and they passively absorb the knowledge. And to help them, we reward them if they get it right and we punish them if they get it wrong. And by this basis, if you're getting rewarded, you're more likely to learn it, and if you're getting it wrong and you get punished, you're more likely not to learn it. So this leads to what we call instrumental understanding. It's quite good if you have to learn to do something quite specific, a behaviour. And there's not a creativity involved, it's more about just being able to do something. Step 1, step 2, step 3, step 4. So for example, if you want someone to learn how to do long division, you can tell them step 1, 2, 3, 4, 5, whatever, actually 1, 2, 3, 4 and repeat. And they can do it, but they just might not have any idea about what they're doing or why it works. So this is the benefits of behavioural or transmission type models. You can get to the right answer more quickly, the rewards are more immediate and immediately apparent, and you can see that you're right or wrong. And really, this makes teaching a lot easier because you can plan it right down. You don't have to worry about what the students think because you assume they don't know anything and you just put them on a track and you guide them through that track. But the problem is it only really is good for learning sort of instrumental things that you want them to repeat and regurgitate. It doesn't develop deep understanding or relational understanding or things like problem solving or creativity. Relational understanding is more about trying to see things in connected and deeper ways. You might call it more conceptual understanding. It's good at finding the connection between different ideas and things like that. And its benefits, it becomes more adaptable to a new task. It's often easier to remember, and having understood it, you can apply it in different ways, but it takes a lot longer. I'll give you an example. Instrumental understanding might be if you said to me, you're on campus here and you said to me, how do I get to the pizza shop? And so I said, go down the elevator, go left, go 100 metres straight ahead, turn right, walk for 50 metres, you'll see a green door, go left there, and then the pizza shop will be 20 metres ahead of you. What I've done is I've helped you get to the pizza shop, but that's all I've done. That would be instrumental understanding. A more relational understanding might be, I say, well, here's a map of the campus. And now here's the pizza shop here, here's where we are, here where we are. And this is how you read a map. And in teaching you how to read the map, I not only have helped you to get to the pizza shop, but to get to anywhere else you want to get to. Of course, teaching you to read a map takes a lot longer than just telling you the direct route. So how do students learn maths? Well, like I said at the start, we don't really know. And it depends on what's being learned, who's learning it, who's teaching it, whereabouts we are, but there's no recipe. And in this course, we're not going to tell you there's any one way to do it. What I hope you do is your students have a variety of ways of learning it. They engage with the mathematical ideas in different ways depending on these things. So, whichever ways you think they learn, just be really good at teaching them in those ways. And you'll even notice between the lecturers who take these different courses and make these videos that we have different ideas. It's not that one's right or wrong, they just serve different purposes. And we don't know the one recipe yet, because we don't think there is one. So, some of you, as you've gone through, would have learned about Piaget. He talks about moving from the concrete to the abstract. When he first developed his ideas, he said at a certain age you can do certain things, and as he moved on in his writings, he did away with the ages and stages of things, but he still kept to this idea of moving from concrete to abstract. So if you follow Piaget's idea, it means that probably even when you start introducing ideas about rates of change and things, you should start with some concrete sort of examples and materials and then move to abstract representations. What we tend to do in senior maths is start straight away with the abstract representations, and we don't give the students the opportunity to develop the conceptual understanding first, which often comes through more concrete materials. Rote learning is something I'm sure you know well. If you've learnt your times tables, you've probably learnt them by rote. And this is the idea that practice makes permanent. This has some implications. There's nothing wrong with rote learning something once you understand it. But if you rote learn something before you've got it right, what you'll do is make your mistakes permanent. So be careful about getting kids to do mathematical exercises before they understand what they're doing. So if you've got some exercises you want them to do about differentiation, make sure they understand what they're doing first before you get them to go away and practice their mistakes. Exercises are not a way of developing conceptual understanding. They're a way of building them and confirming them and making them permanent. Another example is homework. I know in class often we run out of time, so what we say to the kids is go home and do the rest for homework. Now the problem is if you're giving them stuff to do at home in an unsupervised way, they could be practicing their mistakes. So I'd rather they do their practice at school where I can see them and give them feedback and ideas, and at homework they might do some of the more mundane stuff or at least practice stuff that you know they can do well, just to build up some fluency and automaticity. But I certainly wouldn't be giving them new ideas to go home and practice on a regular basis unless I said to them, look, this is a new idea, go home and have a think about it, but we're going to pick it up and think about it some more when you come back and refine it. Learning from experiences, what this means is most of what we do as teachers is make experiences, and then we get the kids to do these activities or experiences, and then we hope they learn something from it. But what we need to do to make the most of these, to make them rich learning experiences rather than just plain activities, is to make sure they notice and note things. It's not enough just to have good maths activities. If you just give kids good mathematical activities, they may or may not learn what you want, but they may learn a whole range of other things, or they may learn errors. So as well as giving them the good activities and tasks, what we need to do is then point out the things we want them to notice and note down, and particularly the mathematical things, so they can generalize them and then apply them to other situations. So here's an example. Translations of functions. We could get the kids to draw the first one and draw the second one, and they could do it on their graphics calculator, or they could do it on a computer software, or they could do it by hand if you want. But what we want them to notice is not just that. We want to put them side by side so the students can see that they're different. So the first one there, y equals x squared, and the second one is y equals x squared plus 3, I think. Now if we just show them, then they may or may not get the idea that the plus 3 just translates the graph up. So what we need to do is help the kids see these things. I'm not saying tell them the answer, point them towards them, see what they notice and note down. Get them to note down, so when they finish they think, oh okay, for any function, the constant on the end shifts the graph up or down. Now this is an instructional model. I've I'll show this before, or you may have seen it already, is when we teach stuff, what we tend to do is we start with mathematical concepts and ideas. We teach them the mathematical concept and idea, and then at the end we get them to apply it to a different context. Now, if the students can do the mathematical context or the concept of the idea, if they can do the basic exercises, and then they get to the problem at the end, which is usually some sort of word problem, whether it's applied, all of a sudden they can't do it. Well, that's because in terms of the activity for the students, it's completely different. And although we can see the connection, often the students can't. So my suggestion is when you do these, rather than starting with the mathematical concept or idea, start with the mathematical problem that contains these ideas or mathematical concepts where they can learn them, then generalise the mathematical ideas, and then they'll be more readily available to apply to other unusual or unfamiliar contexts. There's been a lot of work about brain theory recently, and if you're interested, it's really fascinating to read as a teacher about how our brains work. I'm just going to give you a couple of simple points from this. The first one relates to the memory. Now we know that students, we know there's different parts to our memory. The immediate memory is about 30 seconds apparently. Working memory can last between 10 and 20 minutes. And if you're in a senior maths class, you're probably more like 15 or 20 minutes than necessary, just 10. And then long-term storage is stuff that we've put away that we can recall whenever we need it. Now, when we teach kids stuff, what we're working mostly with is working memory, and then we somehow want them to store it in long-term storage so they can bring it out at various occasions, including the exam. So, a couple of things about this. We know that knowledge will not be stored in long-term memory unless it makes sense and it's meaningful. So often in maths the problem is the students, we teach them stuff and it doesn't make sense and or it's not meaningful. So guess what? They forget. They're not being lazy or mischievous, it just, their brain, the biology of the brain says, don't remember this, it's of no use to you. So it's important then, does it make sense? Can the learners understand the mathematical ideas? What does it have to do with what they already know? How does it fit in? So if a kid says, I don't understand, it's no good saying, oh, don't worry, we'll pick it up again tomorrow. They will forget what we've done. We need to make sure somehow there's something in mind so they will be able to recall it. Some sort of level of understanding. Does it have meaning? Is it relevant to them? Why should I remember this? So often students say, why do I need to know this, or when will I ever use this? Well, we need to be able to give them an answer, so then at least it has some sort of meaning and it's more likely to be recalled. If I just go back, some of the things too about working memory is it's about 15 minutes. So if you've got an activity that goes for a whole hour, or if you're giving students examples and lecturing them from the board for an hour, don't be surprised after 15 or 20 minutes if you've lost them, because their working memories, they have to process that stuff. So something about changing the activities you do every 15 minutes is important. Certainly too, if it's something's in explicit memory, long-term storage, it's experientially based. So you might do things to make it more memorable, use more senses to get things in. So if you talk about translating graphs, for example, you might want them to get them to move their hands around or go outside and physically move. They're more likely to remember it because of the experience it's based in, not just the concept. The abstract concept will be grounded more if it's more sensory rich environment. Now the last thing I want to talk about here is if you're thinking about senior maths, we want them to develop a strong mathematical identity. These kids are good at maths. They see themselves somehow connected to maths. Yeah, a lot of them say, but I'm not a mathematician, or I'm not really see maths in my career. And to do that, it needs to be more than just having good scores and knowledge. So if you think it's got stuff in your head, you need to know math stuff, mathematical knowledge and ideas and concepts. But you also need to have positive attitudes, pardon me, and value it in some way. See it as important. And also, the hand have some skills that you can do, mathematical skills and tasks you're able to complete. And if you think about it in this more broad way, then you know that maths education is not a matter of just transferring the content knowledge from the syllabus through your head into the student's head. Their heart's involved, their bodies are involved, and it means it will change the way you think about students learning. Here's a quote from one of my favourite authors, Parker Palmer. He says, "The teacher who knows the subject well must introduce it to the students the way one would introduce a friend. The students must know why the teacher values the subject, i.e. mathematics, how mathematics has transformed the teacher's life, and by the same token the teacher must value that the students as potential friends of mathematics and be vulnerable to the way the students might transform the subject and your relationship with it." Now, if students are not invited to a valued friendship, then if they're invited, they won't enter unless they are also valued. So they've got to come to mathematics thinking that they have something to offer and something to connect. So as a teacher, perhaps your job is to try and develop a bridge between the subject and the student.